So in this video I'm going to continue to talk about refraction. So here you can see I've got the laser again and it's striking this interface or this surface, and we have our normal line here, and the index of refraction is the same, but let's say I change it to water. You can see that the index of refraction is higher, so the light slows down and it bends towards the normal, right? Now if I did the opposite, let's say I went from water to air, again, remember that the light is going to start to travel faster and it's going to bend away from the normal. Now I can use water and air here, and it says water has an index of refraction of 1.33, but let's say I change it to glass that has an index of refraction of 1.55. Let me do that again and see if you can see what happens to the angles, right? So as I increase the index of refraction, it is changing the angle. So somehow the index of refraction of the mediums relates to this angle, but it also relates, we know as we change this angle, it changes as well. So what this is called Snell's law. Snell's law, which states that as light enters from a first medium at some angle incident to the normal, it's going to be equivalent to that index of refraction related to that angle of the refracted ray. So if we have the interface here, and let's say N1 is air, and light comes in at an angle of, let's say, 50 degrees, and we know that it's going to enter N2, which we'll say for this example is water, okay, that has an index of refraction of 1.33. We know it's going to bend towards the normal just because it has a higher index of refraction. But let's say we actually want to know what specifically is that angle. Well, let's go ahead and just use Snell's law to figure that out. So air, remember, the speed of light moves the same in air as it does in a vacuum, so its index of refraction is 1. So we're going to take 1 times the sine of 50 is equal to 1.33 times the sine of our refracted angle. Right? So in order to solve for this, I'm going to first take the sine of 50 and divide it by 1.33, and that actually gives me the sine of the angle. So to actually get the angle, I have to use sine to the -1 for that value, and I get the angle, refracted angle is about 35 degrees. So this angle right here would equal 35 degrees. Okay. Now, oppositely, what I could do is I could use an angle to possibly determine what type of material that the light is actually shining through. So let's do an example of that. Let's say that we have light, again, striking the surface, let's say at 50 degrees from air. Let's say it bends towards the normal, and this time I get a refracted angle of, let's say, about 30 degrees. Okay? And this is air, and this is something we don't know. So if we use Snell's law, we're going to have 1 times the sine of 50 is equal to N2 times the sine of 30. So I would just take sine of 50 and divide sine of 30. Let's do that. Sine of 50 divided by the sine of 30, and I get, an index of refraction of 1.53. Now we could actually figure out the velocity that substance is moving. So how fast is that light moving through that medium? Or we could look at a chart of index of refraction like you have on your reference tables, and you could see, all right, what most likely is it? So we got 1.53. So if we go through, we would assume that it most likely is crown glass, right? So index of refraction can be, and Snell's law can be used to determine the angle and identify an unknown substance, or the index of refraction can be used to figure out the angle at which something bends as it enters a new medium.